Today we're going to jump right into talking about linear momentum, and it's really just a continuation of our previous discussions on force, as we'll see shortly. Momentum is simply the amount of force that a moving object could transfer in a given time in a collision. We'll talk about how that relates to force here in a moment, but our specific equation for momentum is given by what we see down here, which is simply P equals mv. Now, some things with our equation. First and foremost, P is our symbol for momentum. Despite that not making a whole lot of sense, that's okay. So when we write this in equations, we're going to use that lowercase p as a symbol. Notice that it is a vector quantity. That's what our little arrow up top says. It's a vector, which, as we've learned this year, means that the direction does matter. It's the product of an object's mass times its velocity. And we see that velocity is also a vector. And I think we've mentioned it at times through this year, but a scalar times a vector gives us a vector. And unlike Newton's, which have our fancy kilograms times meters per second squared equaling Newtons, there isn't a derived unit for momentum. It's simply the combination of all of our fundamental units. So the units for momentum are kilograms times meters per second. And that's reflected from our equation mass times velocity, where kilograms are our units for mass, and then meters per second are our units for velocity. This value, this quantity of momentum, it's inertia in motion, and it's a quantity, it's a measurement that is transferred anytime we have a collision. So anytime we have a problem that involves two things running into each other, whether it's a ball running into the earth, whether it's two people colliding, whether it's a car crashing into another car, even into explosions where we have a single object breaking up into multiple pieces and spreading it out into all directions. These are all examples of momentum problems. And being able to describe and explain systems in terms of the momentum involved actually a lot of times makes solving for different variables in those situations a lot easier. Now, this idea of momentum was actually how Newton first described force. And so it was actually described in terms of the momentum. And he said that the net force acting on an object was equal to the change in momentum per unit time, or the rate of change in momentum. And so when we now talk about force equaling mass times acceleration, that's actually a very specific instance of this idea of the net force equaling the rate of change in momentum, where the mass stays constant. And we'll look at where that equation comes from and how it's derived here in a little bit. But this is another important relationship that we're going to need to use this year. Momentum, like energy, as we'll see later, and some other quantities in nature, is a conserved quantity. And so what that means is that in a closed system, so a closed system is one where no outside forces are acting on it, and we talked in our system schemas, we talked about internal and external forces. So in a closed system, there are no external forces, and a lot of this depends on what we define as our system. Because if we're looking at a system where there are outside forces, we can make it a closed system by simply expanding the definition of our system. Or if we want to consider some of the forces as outside forces, we can shrink what we consider to be our system so that we're only looking at individual objects. Regardless, unless there's an outside force, so again, in the absence of an outside force, the total momentum of a system is conserved. Now this means that the total momentum of all of our individual objects before and after is going to be the same. Not necessarily for each individual object, but all of those momenta added together as a whole. Now in our collisions, and we'll come back to this idea of conservation of momentum here in a minute and look at it mathematically, but first let's talk about our two specific types of collisions that we can have. The first is what we call elastic. And if you think about that term elastic, you probably think like bouncy balls or stretching or something like that. And our elastic collisions are ones where there's bouncing, where two objects come in contact, exert forces on each other, and then bounce off or separate. Some good examples of this would be like a golf club hitting a golf ball. Pool balls, if you've ever played pool. Pool balls, when you hit the cue ball and it hits all of the other balls and they go scattering in all directions, that's a great example of elastic collisions. And actually, at a smaller level, gas molecules flying around and interacting with each other, those represent elastic collisions as well. So then the other kind is our inelastic collisions, and this is where they don't bounce off. This is where either before or after the collision, the objects are all a single system or a single object. So it could be two cars crashing together and sticking together, their bumpers get stuck together. Or a great example that you see in a lot of physics textbooks is a train car running into another train car and their latches connecting. Throwing a clay ball at something and it's sticking. And then the other side of that would be when objects start as a single object or a single system, and then after the so-called collision, they become multiple objects. So a bullet fired from a gun is an example of this, where the bullet and the gun are essentially a single object before the bullet is fired, and then the collision is the firing of the bullet, and at that point they become two separate objects. Or something exploding. Anytime something explodes and you have multiple pieces flying apart in different directions, that's another example of an inelastic collision from a conservation of momentum standpoint. Obviously, it's not two things colliding, but we treat it as an inelastic collision when we talk about it in terms of momentum. So, anytime we have a closed system where we identify the momentum being conserved before and after our collision, we can say then that the before and after are the same, which is what we're saying here. But the before and after what? Well, the before and after momentum. So all this kind of fancy looking math means is that the sum of all the initial momenta, which is this piece here, and we mentioned it, but this capital sigma means sum of, right? So the sum of all the initial momenta. So P is our symbol for momentum. The subscript I means initial. So this is our initial momenta. And we say that in the plural because it could be 1, 2, 3, 4, 5, 6, or 100 different objects. And we have to add all the individual momentums of all of those individual objects all together, but not just adding a bunch of numbers. We have to keep in mind that the momentums are vectors, and so we have to add them as vectors. And so that means taking into account direction and adding them as vectors. So all that being said, the sum of all of our momenta before the collision is equal to the sum of all the momenta after the collision, which is what the sigma p sub f means, sum of all the final momenta. We can expand that a little bit more, and this here we're just considering two objects. So let's say we have an elastic collision between two objects. The initial momentum of object 1 plus the initial momentum of object 2 is equal to the final momentum of object 1 plus the final momentum of object 2. We expand that a little bit more into our definition of momentum, and we have the mass of object 1 times the velocity of object 1, initial, plus the mass of object 2 times the initial velocity of object 2. So that's our initial momentum right here. That's equal to m1 v1f, so the mass of object 1 times its final velocity, plus the mass of object 2 times its final velocity. So this statement is always true. The initial and final momenta in a closed system will always be the same. So, quick example. We have a 1 kilogram ball rolling along at a velocity of 2 meters per second. And it's going to have an inelastic collision with a 1 kilogram ball moving the opposite direction with a velocity of 1 meter per second. Okay? After they collide elastically, so let's say elastic collision, that's not an M, right? So an elastic collision, they bounce off of each other, and object 1 travels back in the opposite direction with a velocity of 1 meter per second. How fast does object 2 travel with? So, quick math, we have m1 v1 plus m2 v2. This is our initial momentum. So we have 1 kilogram times 2 meters per second plus 1 kilogram times, and here's where we have to be careful, negative 1 meters per second, because it's moving the opposite direction. Velocity is a vector. So we have 2 kilogram meters per second minus 1 kilogram meter per second. So our total momentum beforehand is 1 kilogram meter per second. So that is a positive value, which means the total momentum is to the right. So after, so PF, we have m1 v1f plus m2 v2f. So we have 1 kilogram times negative 1 meters per second plus 1 kilogram times v2. So we're trying to solve for v2. So we see that this is negative 1 kilogram meters per second. So in order for our momentum to remain 1 kilogram meter per second to the right, this velocity here has to be 2 meters per second, so that the total momentum of ball 2 is 2 kilogram meters per second, and we get a total momentum to the right of 1 kilogram meter per second. Momentum is conserved and everybody's happy. Now, this idea of conservation of momentum is for a system. Okay, and it's important to distinguish between a system and an object. So momentum is conserved in a system, in a closed system. In a closed system, but not necessarily for every object. But not necessarily for each object. So objects, they can have changes in momentum, and hopefully that's obvious, because if the velocity is changing, the momentum is changing, and we know that objects can have a change in their velocity. So that change in momentum that an object can experience is what we call impulse. So impulse is equal to the change in momentum, and our change in momentum is equal to F delta t, and that comes from where we said, remember, that force is equal to the time rate change of momentum, delta p over delta t. So we multiply both sides by delta t. And so the change in an object's momentum is equal to the force times delta t. Thinking about that a little bit more deeply, the change in momentum is related to the change in velocity. A change in velocity is acceleration. That acceleration is caused by a force. So when you have a force exerted on an object over time, you have acceleration, and that acceleration then changes the velocity, which causes a change in momentum. And actually, I want to even be a little bit more specific about that. This change in momentum is equal to F net times delta t. So it's equal to the net force times change in time. We also call that value impulse, which is symbolized with a capital T. So here we have this nice string of equalities. The impulse is equal to F delta t, which is equal to delta p, or change in momentum, which is equal to final momentum minus initial momentum. And this is, again, for individual objects. If we look at our units for impulse, force times time gives us units of Newton seconds. Well, newtons, as we know, is kilograms times meters per second squared. We're multiplying that by seconds. So we should see that our seconds cancel out here and here, and we're left with kilograms times meters per second, which is the same unit as momentum, which makes sense because our impulse is a measure of the change in momentum, and so the units should be the same. Typically, the convention is to use Newton seconds when we're talking about impulse, and kilograms times meters per second when we're talking about momentum, but the two are essentially interchangeable. Now, as with many of our other relationships, we can talk about how this relationship looks graphically and what the graph tells us about the relationship. As we said, the impulse or change in momentum is equal to net force times delta t. We should recognize this hopefully as one of those equations where we can use the area under a graph to tell us what the value is. In this case, the area under a force time graph tells us the change in momentum. Similar to how momentum itself is a vector quantity, the change in that vector is also a vector quantity. And so when we talk about force and time and change in momentum, we have to take into account the sign. And so if it's a positive force or a force in the positive direction over some time, then the momentum change, the delta P is going to equal a positive value. And if it is a negative force, or a force in the opposite direction, then the change in momentum is going to be a negative value, and we have to carefully consider that when finding the total change in momentum. That's all for today. In the next episode, we will talk about energy.